Hi everyone! In this video we are going to go over the Halohydrin reaction as well as the dihydroxylation reaction. So let's start with Halohydrin reactions. And in this reaction we start with an alkene, of course, because all of these reactions start with an alkene. And we're going to actually add a halogen and an alcohol group across the double bond. So we're going to end up with two functional groups, which is really cool that we can do that. We can make a mixture here of functional groups on the same compound. So the way that we do this is we use Br2. Now, again, you can't really use fluorine or iodine. They either react too violently or too slowly. You could use chlorine here in place of bromine. However, chlorine is not used as often because it is a gas. So it's kind of hard to isolate it and use it. But bromine is a liquid, so that's much easier to use in this instance. Additionally, chlorine can oxidize different molecules, and that's not what we want to happen here. So bromine is the halogen that's typically used. Anyway, if we want to add an alcohol as well, then we're also going to use water. So we have two reagents here that we're going to use. All right. So this is going to start out very similar to our halogenation reaction. So we're going to see the alkene coming in and attacking one of the bromine atoms. And then, of course, the shared electrons are left behind on the other bromine. Then the first bromine atom that's being attacked is also going to come in and attack one of the carbons there. So again, similar to our halogenation reaction, we end up with the bromonium ion. Now, you might be wondering, why didn't the water protonate the alkene? Similar to previous reactions where you could add water across the double bond to get an alcohol first. Well, water isn't acidic enough to protonate the alkene in this case. And so we're actually going to see the formation of the bromonium ion first. All right. So now we also have a bromide ion that we formed, and we still have water hanging around. Okay, so now what's going to happen next? Well, you could have an attack by the bromide ion. That can occur to a small extent, but actually the water molecule is going to be a better nucleophile. So it's going to attack the one of the carbons in our bromonium ion. Now you'll also notice that the alkene that we started with was symmetrical, so it doesn't really matter which side the water molecule attacks. We'll end up with the same product. So let's say it attacks that carbon on the right. And because the bromine is on top, the water molecule has to attack from underneath. So this is a backside attack, which is SN2. All right, so that's going to allow us to open up that ring on the top. And we're going to end up with, the bromine off to the left, and then we'll see our water molecule attached off to the bottom right. So bromine and water are opposite each other. So this is anti-addition. Okay, and then we'll also see our methyl groups on either side. I'll just draw them as wedges and dashes to show that those carbons are tetrahedral. All right, so then in the last step, we have to deprotonate the oxygen to make it neutral. So again, there's two different ways you can show this. You could show a water molecule coming in and grabbing one of those protons, or you can just write minus H plus in brackets. All right. And I'll also draw the water molecule here coming in and deprotonating the oxygen, just so you're aware of what's going on. So we would have excess water available to do that. All right, so then our final product has an alcohol on one side and a halogen on the other. And again, this is anti-addition, because the water molecule again has to come in from underneath the bromonium ion, or the backside. Okay, so what if our alkene is not symmetrical? Then which side would the water molecule attack? So let's look at an example where we start with an asymmetrical alkene. So let's just use this alkene where we have two methyl groups on one side and then two hydrogens on the other side, which we're not showing since this is a bond line structure. So what we're really doing is looking at the regiochemistry of halohydrin reactions. So what is regiochemistry? Well, that just means the preference of bond formation. So where would the water prefer to bond? So let's just write that, preference of bond formation. All right, so if we have an asymmetrical alkene and we treat it with bromine and water, we'll see the same mechanism that we saw before. So the alkene, the pi bond comes in and attacks the bromine atom. We leave electrons behind on the other bromine. And then the bromine also comes in, or the first bromine comes in to form the bromonium ion. So we'll get our positively charged bromine here. And on the left-hand side, we have two methyl groups. So I'll just draw those in wedges and dashes, but you could also show them as planar since they're the same group. So it doesn't really matter which one's in front and which one's in back. And again, on the other carbon, we just have two hydrogens, so I'm not going to show those. I'll just leave that empty there. But just know that there are two hydrogens on that right-hand carbon. Okay, and then we know that water is going to come in next. And let's show what happens when it attacks the left-hand carbon versus the right-hand carbon. So we've got red and blue arrows. All right, so if water attacks the left-hand carbon, the red arrow, we do open up that ring. And we're going to end up with a transition state. So let's just draw the transition state here. All right, so let's also draw those methyl groups. Okay, so in this transition state, I'm just going to add some brackets in our little transition state symbol. The bromine is now partially positively charged because its bond to carbon is breaking. And then the oxygen is also partially positively charged because its bond to carbon has started to form, but it hasn't completely formed yet. So it's not a full positive charge yet. All right, and then let's see what happens if water attacks the other carbon, the right-hand carbon. So again, we'll open up the ring. Okay, and let's draw the transition state. Draw in our methyl groups here, and then the water molecule coming in. All right, so again, in this transition state, the oxygen is partially positively charged and the bromine is partially positively charged. So which transition state do you think is more favorable or more stable? So I'll give you a little hint. The carbon that the oxygen is trying to bond to is also partially positively charged. So if that carbon has a partial positive charge, which situation is more stable? Which carbon would prefer to be positively charged? The carbon on the left, right? So let me just highlight that carbon. So this carbon on the left has more carbon groups attached to it than the carbon on the right. And remember, hyperconjugation is what stabilizes carbocations. So the more carbon groups attached to a positive carbon, the more stable it is. So the transition state on the left is electronically favored because there is more hyperconjugation. So that is more stable. Now, the transition state where the oxygen is bonding to the right-hand carbon, that is sterically favored. So remember, sterics has to do with how bulky the molecule is, and the oxygen can more easily access the right-hand carbon. However, that carbon is not as stable because it doesn't have any other carbon groups bonded to it. So it's technically a primary carbocation. So that is less stable. All right, so the sterically favored transition state won't occur because it's just not as stable as the electronically favored transition state. So that one just won't happen. And instead, we'll see our final product where the OH, the alcohol group, has bonded to the side that is more substituted. And then the bromine, the halogen, is bonded to the side that is less substituted. Okay. So this technically can't be called Markovnikov addition because we have two groups that are bonding across the double bond instead of a hydrogen and then a functional group. So, so in this case, just remember that the alcohol group attacks in the second step, and it's going to bond to the more substituted carbon. So lots of things to remember. Okay, so let's talk about dihydroxylation. Now, there are two types of dihydroxylation. There's anti-dihydroxylation and syn-dihydroxylation. And what we're really doing with this type of reaction is we are adding two alcohol groups across a double bond. Addition of two alcohol, oh my gosh, I can't spell today, of two alcohol groups across a double bond. And again, you could either have them add on the same side, so above or below, or on opposite sides where one alcohol is above and one is below. So let's talk about that case where they'll add opposite to each other. So that's anti-dihydroxylation. And let's say we're starting with cyclohexene. So we've got a double bond in our six-membered ring. And the way that we're going to add these alcohol groups opposite each other is by first using something called MCPBA. All right, so the reason that we abbreviate this chemical is because it has a very long name. So MCPBA stands for meta-chloro-peroxy benzoic acid. So it is a very long name. MCPBA. Meta-chloro-peroxy benzoic acid. But you can just call it MCPBA. That's okay. All right, so the second step involves an acid and water. All right, so the products that we'll end up with are the following. So in one case, we will have the top OH in a wedge, the other one's in a dash, but we could also have the enantiomer of that. And in fact, we end up with a 50-50 mixture of enantiomers. All right, so again, this is anti-addition where they add opposite across the double bond. Now, why do they add opposite each other? So let's kind of walk through the mechanism. So in the first step, again, we're adding MCPBA, and what happens when we add this chemical is we get something called an epoxide. Let's see. So let's see if I can draw this. There we go. So an epoxide is an ether. So remember, ethers have an oxygen between two alkyl groups. But an epoxide in particular is a three-membered cyclic ether. So we have oxygen and 2 carbons in a ring with each other. All right. So then in the next step, we add again an acid and water. And what ends up, oops, that's not what I was trying to do. What ends up happening is the oxygen grabs onto a proton from the acid and it becomes, let's see, the name is, it's just a protonated epoxide. I thought there was a fancy name for it, but I think it's just a protonated epoxide. Okay, so now we've got a hydrogen attached to that oxygen, and that oxygen is now positively charged. And then additionally, the water molecule is going to come in and attack one of the carbons in our epoxide and open up that ring. So let's just show, I guess it doesn't really matter which side because it can attack both sides equally. So the water molecule will attack one of the carbons, open up the ring, and again, it could attack the other side as well. So that's what gives us the 2 enantiomers. Now, this does need to occur from behind the epoxide. So this is a backside attack, and that's why we end up with OH groups on opposite sides, because we just showed that the epoxide is above the plane of the ring, and then that means that that side's blocked. So water has to come in from the other side. Okay, so then we'll end up with an alcohol group on one side, and then we have our water molecule on the other side, and then we just need to deprotonate that to get our final products. Okay, so again, if you use the MCPBA chemical, that is going to give you an anti-addition of alcohol groups. But what if we want these alcohol groups to be syn to each other, so on the same side? So we're going to have to use a different chemical. The one that is most often used is one called osmium tetroxide. So osmium is OS, and then we have 4 oxygens bonded to osmium. So osmium tetroxide. All right, so one issue though with using osmium tetroxide, it is toxic and hazardous. I believe this is a chemical that can make you go blind. It interferes with the rods in your eyes, if I recall correctly. So there is another chemical we can use. I'll show you that in a second. But the other chemical has issues of its own. So, you know, you can't really win here. You just have to be careful. But in addition to osmium tetroxide, we would also use sodium sulfite or sodium bisulfite. Either one is fine. So I'll just write sodium bisulfite. And then we have water as well. And again, this is going to give us addition of our alcohol groups on the same side of the ring, so either above or below. So if we do have addition from below, what is the relationship between those two products? Are they enantiomers, diastereomers, or identical? They're actually identical. So you could rotate one of those and end up with the other molecule. Or the other way to view this is that there is a plane of symmetry. So this is actually a meso compound. So in this situation, we don't have enantiomers that form. We just have one compound. All right, so let's talk about the slightly safer chemical that we can use to do this same reaction. So you could also use something called potassium permanganate. Let's see. So with potassium permanganate, we also need to use sodium hydroxide, and this does have to be performed at really cold temperatures. So I'll tell you why in a second, but we end up with the same exact product. So the alcohol groups add on the same side. Now, the reason we need really cold temperatures if we use potassium permanganate is potassium permanganate is an oxidizer. So if the reaction is at all warm, then oxidation will continue to occur beyond the alcohol groups and will actually end up forming carboxylic acids. So let's just make a note of that. If temperature is warmer, oxidation continues to carboxylic acids. So, I mean, later on, when we do talk about carboxylic acids and how to synthesize them, we could use potassium permanganate at warmer temperatures. But if you perform this at colder temperatures, you can just isolate the alcohol groups, which is nice. Okay, so I think we'll stop there for this video. I don't want to overwhelm you with all of these mechanisms and such. But in the next video, we will talk about ozonolysis. So we'll get to see what happens when you add ozone to an alkene. And then we'll also talk about hydrogenation, where you can just add hydrogens across the double bond, which is super useful. So I will see you then.